Hello. Our group consists of Mark, Justin, and myself, Sarah, and over the term, our project was on detecting pitch correction in popular songs. So I'll start off by introducing our project and explaining some of the foundational research and methodology. Our goal was to detect and visualize pitch correction in both old songs and popular songs because tools like Autotune and Melodyne are often used subtly, but they can also be applied heavily, which impacts the authenticity in performances. We were inspired by Wings of Texas, and we wanted to approach this in a more structured, analytical way on a larger dataset. So we began by reviewing the theoretical foundations. Pitch correction involves three stages: pitch tracking, modification, and resynthesis. Detection can be hard at times, but prior research shows that spectrograms and pitch contour plots can reveal little things like unnatural steps or straight pitch lines. We then developed our own dataset by combining studio and live vocals from two main datasets, Muse 18dB as well as Vocal Set. We used the Splitter model and we separated vocals from background audio. And this step was really critical because any leftover instrument harmonics could interfere with pitch estimation algorithms, and Justin and Mark will be going into more detail. So I'll pass it along to Justin now for evaluation.
Thank you, Sarah. In our evaluation, we focus on two areas: visualization and detection accuracy. For visualization, we judge effectiveness based on clarity and interpretability. We ask questions like, does the pitch contour match the expected vocal range? Are unusual patterns easily noticeable? Since we use Python, we also compare different visualization libraries to find the best fit for our needs. On the analysis side, we wanted to evaluate how well our detection algorithm performs compared to human observation. To do this fairly, we created a dataset of raw, mildly corrected, and heavily corrected vocals. These samples were tested in parallel by both humans and our model without knowing which were corrected. And I'll pass to Mark.
So I'll be walking through the code. This is one complete data generation example with Pink Floyd. Right, the first thing we're doing is extracting the vocals using Splitter. Then we're using Solero to remove the silence to prevent data corruption with black spectrograms. And then we are using CREP to predict the fundamental frequencies. And then we use Librosa to plot the spectrograms and also the pitch contour plot overlay. And I believe this overlay would accentuate the features that we want our model to learn. And afterwards, we segment our images into 10-second segments. As you can see, this is what the actual data set looks like. And then afterwards, right, we do some plotting here. And then after we auto-tune the same songs from our data set, right, and then also generate a data set from that. And this is an additional plot to see the amount we've pitch corrected. And then, yeah, let's go through the model, right? The model, first off, starts with data augmentations like random cropping, flipping, and normalization, and basically organizes it into training and test sets. And then this is the main training loop, which flips between validation and training. And more importantly, the model architecture, we are using a ResNet 50 with the final layer being replaced for binary classification. And the training started off with the last layer being, with every layer being frozen except for the last one, and then using ResNet as a feature extractor for transfer learning. And then afterwards, we unfroze some of the later layers, right, for better model fine-tuning with sliced learning rates. And we were using checkpointing to get the best model. So the main data set that we had 19,000 images, and we tested our model on 7,650 10-second clips for a test accuracy of 76%. And afterwards, we tried training just on the vocal set part with 7,746 training images and 2,000 test set images, and we were able to achieve a 97.8% accuracy. And here I'll do a one-shot demo with a song that is very auto-tuned. As you can see, 95% of segments are auto-tuned. Mildly auto-tuned, right? 70% of segments are auto-tuned. And then also a live performance, right? As you can see, 0% of segments are auto-tuned. And this does actually reflect the songs, right? As you can see, Boom Boom Pow is very auto-tuned. And then you have Coldplay, which is still quite auto-tuned, not as much. And then we have, lastly, the live performance. So as you can see, the model actually works quite well here. I'm going to pass it back to Sarah for the conclusion.
So at the end here, we also kind of wanted to talk about our project from a social aspect. In the future, we want to consider things like how pitch correction varies across time and genres. Our initial hypothesis was that older music tends to be less corrected, which supports the common belief that it's more quote-unquote authentic. And we also speculated that pop music relies more heavily on pitch corrections, such as Boom Boom Pow, like we just showed, because of its commercial nature. And in the future, we want to test this by comparing correction rates across genres using different types of statistical analyses and visualizations. This finally led us to some deeper ethical questions, like Justin touched upon earlier. So, as software makes perfect singing more accessible, where do we draw the line between enhancement and deception? And how does this change how we value vocal performances? This was mostly just some food for thought in our report when looking at things from the bigger picture. So in conclusion, our model was trained on two main datasets of 150 songs, and we generated approximately 27,000 images based on their data. We hope that our work sparks future research into both the technical and the cultural impact of pitch correction. And with that, thank you so much for watching and have a great day.